Let's connect functions in series. Very interesting. We're going to start with whatever we know, and we know geometric series first. So intro comes with geometric series. That's why we push it so hard. It's actually a very nice intro to many topics in the series chapter. So the thing is, what we know is how the geometric series looks like. It's a coefficients in front, r to the n. N starts from 0 to infinity. It converges to a finite number if r by absolute value is less than 1. And it converges to a number we know. It's a first term, 1 minus r. If and only if r by absolute value is less than 1. This is a geometric series. This is not a new material. We already tested you on these ideas. But from here, you know what I'm going to do? I'm going to do some very interesting, cool thing. I will substitute and I will say let's us make a to be 1, why not, and r to be a variable x. So from here, what we're going to have, this is too early. From here, what we're going to have will be, this is really cool idea. It will be still a sum, not so fat, a sum x to the n from 0 to infinity. So now we have a variable instead of r. R was some kind of number, preferably from -1 to 1 in order to converge. X now can be any real number. And it will converge to 1 over, because the first term is 1 minus x if absolute value of x is less than 1. This is not supposed to be so ugly. 1 minus. That is the power geometric series. It's called power geometric series. What is the difference? Now we have input. This is not new, we had it before, but what is new? Using ideas of calculus, we're going to define something pretty interesting. So let me give you some intuition, and then this formula comes in. So we're going to, since we're making this equal sign between a series and a function, 1 over 1 minus x is a function. We learn in calculus 1 how to find when it's increasing, decreasing, have concave up, concave out interval, points of inflection. It actually has horizontal and vertical asymptote, everything. We learn everything, domain. How in the world it's connected to the series? Series is sums coming from sequences, which is literally a data set. So that's a very cool idea. Since we're making this equal sign between series and a function, this is so beautiful that we have this equal sign. That brings into the picture the calculus, which is derivatives and integrals. We're going to call it operations on power series. Operations on power series. Like I mentioned before, the convergence set is extremely important because convergence set tells us where is a safe space. And only we can use operations on power series on the safe space, which is convergence set or interval of convergence. Let's call this beautiful formula S. S will be a series a sub n x to the n. N is from 0 to infinity. We can even write down the terms if you want. We can write down the first 4 terms, for example, just to see how it looks. The first term you plug 0, a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub 2 x squared plus a sub 3 x cubed. And good enough, keep going forever. This is infinite power series. From here, we'll have what? We will say then for x that belongs to I will explain in a second if you don't know what is this sign means belongs. That belongs to I, which is a convergence set, convergence interval or convergence set, that's the same thing. Do you know what the sign means? It's C with a tongue inside, means belongs, or you can write down in. X belongs to real numbers, right? So that's the idea. C with a tongue, belongs. I keep thinking that you're raising your hand because you have the hand. No, you should keep it. But it's funny that I keep seeing the side vision that you have a hand up. A pink, very pretty hand. We're going to differentiate. Look at this. This is going to be so cool. We're going to differentiate S. And we're going to integrate it as well. So we never done it before. We never differentiated or integrated serious. So now it's getting serious. Because we're literally taking hardcore, well, it's not hardcore yet, calculus into this. And now think about a second derivative, third integral, use substitution with serious. How cool is that? Let me explain to you very slowly. Listen to me very carefully. From 0 to infinity, I'm putting a huge prime. So I'm going to differentiate this series. There are two ways you can do it, which is the same idea, but somehow students usually choose one or another one. The first one, we're going to just do it. Just do it. And then I'm going to show you how to do it step by step. Let's see. Remember that sums means we're adding things together, right? It's addition. We keep adding things all the time. Lots of things are being added. So we're going to differentiate the sum. We know how to differentiate the sum. Moreover, it's, well, I will show you later what I mean by moreover. First, we're going to just see it as it is. The sum, this a sub n is multiplied, and it's a constant, so don't touch it. It's multiplied by x. So it's a rate. And you remember derivative of 5x is 5, so we don't cancel a sub n. Now, what is happening with x to the n? It's the only variable I see, so there's no product rule. N goes down, x to the n minus 1. That's what's happening here. Now, we lost the first term. As you can see, n now starts with n minus 1, so we're going to move one counter to 1. N used to be from 0, now n is from 1. I will show you specifically why it happened. We lost the first term when you differentiated. Let's see why. Let's see why. Now, instead of doing it as a sum, let's do it term by term. Put equal sign. This is term by term. The answer will be the same, but somehow students like to choose one or another one. Term by term. I will be looking at this right-hand side part. Right-hand side. And I will be differentiating it term by term. What is the derivative of a sub 0 if it's a constant? 0, right? Plus, what is derivative of a sub nx? a1, exactly. X gives you 1. What is derivative of a sub 2x squared? 2a2x, exactly. Let me show it. This 2 comes down. You can put it in front of a2 if you want. 3 comes down. What is going to happen? 3a3x squared. Thank you, exactly. Plus, and keep going. As you can see, the first term is gone because now everything starts with 1. So that's why my counter also is shifted to the first one versus to the 0 term. So we learn how to differentiate it, either term by term, or you actually perform in the sum notation. When I was a student, I liked term by term, and then with experience, I actually realized this is easier. This way is easier. Somehow we're just afraid to look at the sums, but actually doing it right away have less mistakes. So I prefer you to try to do it this way right away. And I'll be kind of trying to push it, but if you do it term by term, it's fine too. 2, okay, if we learn how to differentiate, then let's integrate. Integral, let's do indefinite integral first of s sub x. We're integrating the sum a sub n x to the n. N is from 0 to infinity. And then we also need dx. So you can put parentheses if you want, but actually you don't have to. There's no restrictions on that. So you can show this to your parents if they ask you what do you do in classes. Show them this. This is actually pretty awesome. You see? Like, come on. Very nice. Scare them on the Halloween. Then we're going to integrate that. Again, let's do it right away, and then let's do it term by term. Right away will be, I know it's going to be a sum, because we're adding things, we're integrating them, we're adding them again. Just something different will be there. Don't touch a sub n. That's the rate. It's going to stay there. What happens with x to the n this time? Yes, x n plus 1. What else? Divided by n plus 1. N is from 0 to infinity. We did not lose anything. What else? Did we miss anything? Plus c. Don't forget plus c because we're integrating, right? So now we can actually write it down term by term, which is pretty interesting. Check it out. If you do it term by term, I'm going up to the yellow box again. Integral of a sub 0 in terms of x will be a sub, so, okay, skip some space. Skip the space. A plus a sub 0 x came from a sub 0. What is the integral? Maybe I should like point out. What is the integral of a sub 0, a sub 1 x? A sub 1 what? 2 over 2, exactly. Square over 2. Do you all agree? It's a little bit tedious and annoying, but it's cool if you can participate. Then A2. A2 will be x to what? Let's move out. Cube over 3. Let's do one more. A sub 3 is x to the 4 over 4. Keep going. What is missing? Plus c. But since c is a constant, it's actually nice to put it at the very beginning. C plus. And now we don't lose any coefficients. You see, we have a x to the 0 coefficient, x to the 1, x squared, x3. So they all are sorted very nicely. Even the original coefficient constant is in front. So it looks very nice. What do you think about this? So either terms or the whole sum. Yes?
So we take the derivative and we have to make, instead of n equals 0, n equals 1, do we ever make it n equals -1?
Good question. Sometimes we do, but in this case it's not necessary. When n, oh, actually maybe it is. When n is 0, we should start. Yes, he's right. Good job. Very good point. I have to check if it matches. The equal sign should be checked. In the previous one, I checked and I realized if I start with 0, I will have 1 over x situation because x to the minus 1 is 1 over x, and I don't want that. So I changed to be x to the 1. X to the 1 gives you x to the 0, which is this term. So to get x to the 0 here, I need to change it to minus 1. Very good. Good job. And now I can check. If I plug it, it's going to be x to the 0. Oh, but then I divide by 0. Oh, that's why I did not do it before. I see. No. Now I can see actually what's the problem. Keep it at 0 just because we don't want the denominator to be 0. But you know why it still works? Because of this c. So c will be standing outside no matter what. Yeah. Okay, that's actually too bad. This is the first term. The whole thing is the first term. Good question. Those are tiny little things which usually are proved in the theorem. Thank you. Here it is. This is the theorem. Please copy it. But basically, this is an important idea which you just need to understand. You don't have to memorize it. Idea number 1. If f of x is a sum, this time we have a shift. C sub n are my coefficients, and then I have a shift. X minus a to the n. It has a radius of convergence greater than 0. So r is better than 0. Then I have two formulas. The first one is how to differentiate this series. Well, it's a power series, so we're using power rule, which means n goes down, x minus a times n minus 1. Moving on. And we can integrate. We can also integrate this series. As you can see, series is written in terms of a function, but we're basically integrating a series. If we're integrating a series, then you have x minus a to the n plus 1 divided by n plus 1 and c in front. Yeah, let me wait for you to write it down. Interestingly, we also have the theorem that says both of them have the same radius of convergence. These also have the same radius of convergence r. So each will have the same r. That means when we differentiate or integrate, we did not ruin this safe space. It's still going to be the same r. Very cool idea. Okay, and now we're going to have examples. Why this is so important. You'll be pretty impressed in some kind of stuff, which is very interesting. The importance of this is to create more functions out of series, or more series out of functions. And then people use one or another one in lots of applications. Example. Let's stick to the very original one, which is geometric series. Geometric series, let me write it down and put it in the fat box. So it's going to be 1 over 1 minus x. This is the result of the geometric series, which was called x to the n. N is from 0 to infinity. Put this in the box. It will be one of the most important things to apply. It's a very applicable idea. This happens only when x is less than 1 by absolute value, and this is coming from geometric series. Power geometric series. Left-hand side is a function. In this case, right-hand side is a series. We're going to be using this function. So use this function. Let's call it a star. This whole formula is a star. It's pretty important, so it deserves to be a star. Use to find series expansion, or just series. Let's put expansion. Expansion for. And now we give you some kind of random functions. For now, of course, we're going to give you the functions we think you will handle. 1 over 1. I don't like this example. Let's do first plus x. This one. So if we have 1 over 1 minus x, how to figure out the series from 1 over plus x? You can always ask me, who cares? I'm so tired and I want to eat. It's almost noon. Almost noon. But the thing is, it has lots of applications, which I keep mentioning but never show you. I will try to show you next time. Which is the case. Series are so cool. If you put this equal sign, it takes you to the programming and computer science and C++. It takes you to data science and image processing and AI. And that's why we want to have this equal sign. What is here? Actually, put the question mark. Like, what is here? I would even say, what is over here? Like so. Like, what is the series going to be for 1 over 1 plus x? Okay, let's see. Solution. Check out this clever mathematical idea. 1 plus x can be written as 1 minus x, right? How? Minus minus. Like, duh. Very interesting, but many clever ideas in math are actually very simple. And then from there, it becomes like triple integral right away. But these clever ideas made lots of cool steps. Minus minus gives you plus. And now it's literally use substitution, just not integration kind of use substitution. You copy minus x and plug it everywhere you see x. That's my new input. Instead of x, we're going to have minus x. We're going to have some minus x instead of x. To the n. N is from 0 to infinity. Does that make sense what I just did? I will show you this little arrow in yellow, or maybe green. Here. Instead of x, my new input now is minus x. It's literally use substitution here. Maybe I should even show. It's just we don't integrate. Use substitution is not only reserved for integration, use substitution. Use substitution in general is substitution. So, usually people don't leave the answer like this. They rewrite it as minus 1 to the n, x to the n. Let me know if you agree or disagree that that's the same thing. Usually people don't keep the negative sign inside with the function. They take it out. Why? So I'll write down like so. 1 over 1 plus x. Put this in the box. This function will be extremely helpful in your homework and the test. This is the second function. Comes from the star. So from the first star, we have this new formula. They usually go together, first star and the second star. Because it has a negative 1 to the n sign, it is an alternating series. Alternating. Because it alternates the sign. Series. Because it alternates the sign. If you start actually rewriting it down, it will be plus minus, plus minus, plus minus, plus minus. Alternating series. This is a pretty makes sense definition over here. What do you think about this? Not too bad. Example 2. Okay, if we got this function, how about 1 over 1 plus x squared? How to find series for this function? We only for now know geometric series equation, so we're gonna use that formula star. So again, the idea will be the same. Solution: 1 over 1 plus x squared. We need minus. Let me go back to the box. Here it is. Let me put in a rainbow box. It's actually that important. Here it is. It's very important. Fat rainbow box. So I need 1 over 1 minus x, but I have 1 over 1 plus input. Instead of x squared, we'll say input. So the first trick is exactly the same. 1 over 1 minus. What is the input? Minus x squared. Boom, you're kind of almost done. This is your new input. This is your new u, if you want to see it this way. The original formula was x to the n, or input to the n. This one is minus x squared to the n. N is from 0 to infinity. Agree or disagree? What do you think about this? This is what we usually put in a test, something like this, and somehow it's very confusing at first, and then people get it somehow. We don't leave the answer like this. Usually we rewrite it and simplify. Check it out. We will have sum, take out the negative 1n. I kind of call it, release it. It's like here stuck in those big parentheses. Usually it's not convenient. To show it's alternating, we like to put it outside. So release it from those parentheses. Now what's happening is x to the 2n. Because x squared raised to the n is x to the 2n. N is from 0 to infinity. Very interesting. Did you notice it's raised to the 2n power? That means it's even. Because no matter what my input is, I will square it. Let's check. That's where the even and odd functions come into the picture. And we're going to talk about sine and cosine very fast. Actually, soon, on Wednesday. Let's check the terms, if I'm right or not. When n is 0, what is my first term? When n is 0, then when n is 1, then when n is 2. What is my first term when n is 0?
1.
1. Let's check. Minus 1 to the 0 is 1. X to the 0 is 1. Amazing. The next one, n is 1, gives you what? Minus. Because minus 1 to 1 is minus. So we know it's alternating. If the first one is positive, the other one will be negative. And now you know the pattern. I don't have to actually keep calculating minus 1 all the time. I know it's alternating, so it changed the sign. Actually, let me write it down for you. Every time you see minus 1 to the n, that's called alternating series. Alternating series, because it alternates the sign. In a sound system, you can imagine. High and low, high and low, high and heartbeat, high and low, and so on. So this, and when n is 1, what is a term? Who knows? X squared, minus x squared, right? Do you agree? Then what's going to be when n is 2? X to the 4. When n is 3, minus 6. When n is 4, x to the 8. And now you know the pattern. You see? You already can see the pattern is keep going. So these are your homework problems at the very beginning. They are not so bad until we're getting into differentiation or integration. So this actually is a pretty important function. Example 3 hops on top of the example 2. Find the series expansion. Series for the integral of 1 over 1 plus x squared dx. Very interesting. Why do we care? Why do we care to integrate 1 over 1 plus x squared? We do know the integral for this function. What is that? Solution. We know And I'm like very bravely saying, do you know? What is the integral of 1 over 1 plus x squared dx? Arctangent, good job. I will write down tangent minus 1 because it's fancy to write. X plus c, don't forget that. This is your mastery exam calculus 1 class if you took it at this school. Or just calculus 1 class. So we know that's going to be the answer. But we also know the series expansion. We just found it. We also know that 1 over 1 plus x squared has an expansion. We just wrote it down. I will put it in the box for you maybe. This one. Minus 1 to the n, x to the 2n. That's an equal sign for the 1 over 1 plus x squared. The sum minus 1 to the n, x to the 2n, n is from 0 to infinity. We also know from the previous example, example 2, right? From example 2. So we know how to find expansion for the integral. What is going to be the expansion for the integral? We will integrate this sum instead of figuring out everything from scratch, which I also will explain you how to do that as well. So, thus, therefore, to summarize, what other GRE words do you like? That's what I learned when I was preparing for the exam, GRE exam. So we're going to integrate this sum minus 1 n x to the 2n, n is from 0 to infinity, dx, to find the series expansion for the new function, which is integral of 1 over 1 plus x squared. We're going to do it right away. I do recommend to learn to do it, how to do it right away, not term by terms. But then I will show you how to do it term by terms as well. Let me write down on the right. Check it out. It's going to be a sum. Don't touch the coefficients. Just copy them because they're just standing there. You don't need to do n plus 1 over there. That is a coefficient. If it's 5x squared, the integral of that is still 5 times something new. Then the part that's changing is actually x to the 2n. So it's going to be x to the 2n plus what? Plus 1 over 2n plus 1. It's a power rule. N is from 0 to infinity. That is the series for the integral of 1 over 1 plus x squared. Why it's important? Because we just found IA, or therefore, thus. I would just do one more thus. I don't know, not very creative. Put something more beautiful than thus. Thus, arctangent, or tangent minus 1, let's be consistent. Tangent minus 1 of x, we forgot plus c, is the sum minus 1 to the n, x to the 2n plus 1 over 2n plus 1 plus c. So we just found right now the series expansion for arctangent. How? Because we knew that arctangent comes from integration of that specific function, which is 1 over 1 plus x squared. It's kind of a bit iffy and confusing. The idea is we try to find series expansions for important functions. Of course, we figure out something classical, like 1 over 1 plus x will be classical. If you integrate this, what is it going to give you? Log. If you integrate 1 over 1 plus x, it's going to give you a logarithmic function using u substitution. So now we know that if you put integral on both sides, actually it's like so, right? Or like so. Then it will be this answer for the logarithmic function. If you differentiate, it gives you something like this, or 1 over 1 plus x squared if you differentiate. And then you figure out the series for that. In this case, we even jump into trigonometric functions, arctangent. And at some point, which is on Wednesday, next class, we're not done, but I wanted to make a link. In the next class, I will show you this interesting idea, which we're going to call Taylor and Maclaurin series, and it's going to be a whole beautiful, amazing table. This is a table. We're going to learn together all the important, not all, the most common functions. We just learned 1 over 1 minus x, that is geometric series. We're going to learn how the series for e to the x. Trigonometric functions comes in. We already did arctangent. Logarithmic function comes from the very beginning. If I integrate 1 over 1 minus x, I get logarithm. And we just found arctangent, which I will add to the table. This is a classical Taylor series, which also called basic Maclaurin series. That's going to be the most important chapter, is topic of this whole chapter, those series. We used to enforce you to memorize them all by heart, and then I pushed not to do that anymore. So now we don't force you to memorize. Moreover, you will have this table on the test, because I was pushing that too, and then it was successful. But not everyone likes this idea. Many professors think that you have to memorize them all because of how important and amazing they are. But you know, some people have bad memory, okay? It's just kind of discrimination not to think about that, I feel. So let me show you example from homework, and then you can start the whole chapter and just do amazing work there. This is actually number 2 from your homework. Example 4. Let's find the expansion for the function f of x equals x squared 1 plus 2x. So we're looking for expansion for this function. That's like a dumb way to write it down. Sum of what is that? But in the homework, you'll see they say very professionally, find the series expansion for the given function. Solution. For now, we only know geometric series expansion, which is a formula star. Rewrite it. The more you rewrite it, the better you remember it. We know that 1 over 1 minus x. Do you remember how it came from? It came from the x to the n being geometric series. And we know geometric series converges to the first term 1 minus x, which is a common ratio. That's how you memorize it. That's how I memorize it too. So this is the formula star, power geometric series. This formula only works when x is less than 1 by absolute value, from 0 to infinity. We will try to match the function we have with the one we know. So solution, x over 1 plus 2x. My function on the left in the blue color doesn't have any x in the numerator. So I'll just put it x times. Is it x? I kind of want it. Oh, it's x squared. Yeah. I was like, I don't remember it being x. Fix it to square. Take this x squared out, and you will have 1 over 1 plus 2x. Now I already have 1 and 1. At least that matches. Both functions have 1 at the top. I need denominator to be 1 minus input, but I have 1 plus 2x. The same trick works. It will be 1 minus the input minus 2x. Minus gives you plus. Check it out. It's kind of like so clever, but like so stupid. It's very interesting that how simple it is, but actually it makes so much sense to do to go to the upper level math. Does it make sense what I did? X squared, kick it out, and then 1 minus stuff. This stuff is your new input. Everywhere you see x, now it will be minus 2x. So I have x squared waiting outside. The sum is input to the n minus 2x to the n. I'll even write it down for you. Input raised to the n. And my new input is input. My new input is minus 2x. Does that make sense? Input to the n. N is from 0 to infinity. That is not enough. I need to have like series with a stuff inside of it. So let's put equal sign. And then submerge. Well, actually it's distribution. Submerge x squared inside of the sum notation. Because sum or series is a sum, sigma notation is a sum, x is multiplied by the sum. It's basically we're distributing it, you know? We're distributing it by multiplying by infinitely many terms. So that's why it's possible. We can do that. Still not good enough. Okay, negative sign tells me it is an alternating series. So I will put sum minus 1 to the n because I see the negative sign right away. So I'll put this in the notation minus 1 to the n. Make sense? Maybe a little bit too fast, let me know. 2 to the n. And x. What's happening with x? X squared and x to the n. That's what we have here. from 0 to infinity. Should I reorder it back in the original order so you can see what's happening? Well, you can keep it as it is, but if you don't understand it, let me rewrite it in the original order. X squared was first, minus 1 to the n, 2 to the n, x to the n. That's what's happening. I am breaking this n into those three factors, minus 1 to the n, 2 to the n, x to the n. Now I'm collecting the terms. The classic notation is to put constants first, coefficients first. Minus 1 to the n, 2 to the n. That goes first. Times x, n plus 2, or 2 plus n. N is from 0 to infinity. That is the final answer. So I'll put it in green color. The function x squared over 1 plus 2x has an expansion that looks like so. Minus 1 to the n, 2 to the n, x to the 2, n plus 2. One more thing left. We will ask you to find the new convergence set. The thing is, the original restriction was x by absolute value must be less than 1 because it's the input. My new input now is this, minus 2x. So converges for, or in general, this equal sign only possible for minus 2x less than 1 by absolute value. Make sense? Then minus 2x is from minus 1 to 1. Divide by minus 2 changes the, let me do it slowly. When I divide by minus 2, I have to change each nose of the inequality. Remember that property? Maybe if you don't, it's fine. It was a century ago you learned this. But it means not only I'm dividing by minus 2, it will be minus 1 over minus 2 is 1/2. X inside minus 1/2. People don't answer this way. So now you flip it back. When you flip it back, you reverse the order. Remember, the nose points at the smaller one. You guys, and Americans learn, I know how you guys learn. You say, the open mouse eats.
Yeah.
What does it say?
The alligator.
The alligator eats the what? The bigger one. The alligator eats the bigger one. That's, yeah, I know this phrase. Almost. 90% I remember it. The alligator eats the biggest one. We were taught it as a little nose. Nose points at the smallest one. That's how I learn. Doesn't matter. The way you learn is good. Just make sure you know how to do it. Convergence set. Convergence set, which means this is only where we actually could differentiate and integrate. And just in general put this equal sign. It's from minus 1/2 to 1/2. Radius is 1/2. Center is 0. So these are the questions. We'll still keep working on these questions. What do you think about that? A little bit, lots of material today, understand that. It's like Monday hardcore class. On Wednesday, I'm going to slow down, show you more examples, your homework, and then we're going to have quiz on Friday on the previous material, which is ratio test. Maybe a little bit of this for extra credit. Do you want to come here to ask a question? Thank you. Good job, people.